Thank you for coming. Well, yesterday we've been more or less at this point here. So, please let me briefly remember what we tried to do during the first lecture. We started from some general statistical problem, which is to check if the conditional expectation of some variable epsilon. Excuse me. Should we wait a little bit till everybody will come, or?
No. I think that nobody more will come.
Okay.
I think so.
Okay. By the way, I think now you have the slides on the website of your lab. I sent it yesterday today, very early in the morning, to Spokojnie, and he said that he asked somebody to put it on the website. So you may find the slides there. Okay? Well, early in the morning because there is 3 hours of jet lag, so it's complicated. Especially when you go to bed very late. So, and jet lag not in a good way, in the bad way. Because I'm not sleeping during the night. Okay, let's go to our problems. So we started by stating a statistical problem under the form conditional expectation of some variable epsilon given a vector x of dimension q is 0 or not. And I tried to persuade you that this problem is rather general in statistics, in regression-like models. And we gave several examples where this the statistical problem of model check can be brought down to checking the nullity of some conditional expectation, typically of the residual given the covariance. And we started to talk about some possible approaches and in all these approaches, the idea was to transform the conditional expectation problem in a marginal expectation problem. Why marginal? Because marginal expectation could be easily approximated by empirical sums. So in some situations, we distinguish two major approaches. One of them is to take many expectations indexed by some variable, small x, it was the case here, that lies in a domain in a Euclidean space. This was one approach. The other approach was to use some unknown functions and to write the initial conditional expectation problem in a marginal expectation problem using this unknown quantities. Okay? It's clear, everybody follows. And when you take many expectations, what you get when you replace expectations by empirical sums, what you get is a stochastic process. And then you have to look at the behavior of this stochastic process and to build test statistics like Kolmogorov, Smirnov type, or Kramer from Mises. And this was the approach that we studied, we briefly mentioned, and we said that this has some drawbacks, some advantages. And the alternative was based on this unknown function, and this unknown function has to be estimated non-parametrically, and for this purpose I propose to use a kernel estimator, and then the test statistic finally that you obtain is a double sum, or a so-called U statistic, and the behavior of this U statistic is given by a central limit theorem for degenerate U statistics. I don't think I said what degenerate means. I promised at some point, but I think I forgot. So, if you have a let's say this is a U statistic, then you would say that the degenerate if expectation of f zi zj given zi is equal to the expectation of h zi zj given zj and is equal to 0. Then you say that the U statistic is degenerate. Okay? And then the case, in fact, U statistics that are degenerate are extensions of the empirical process. This is of order 2 because you only use pairs of the observations. So Zi, Z1, Zn, IID sample. And what happens usually with these degenerate U statistics is that they behave like the rate of convergence of some this U statistics is something like n to the power k over 2, where here k equals 2. This is the U statistics of order, this is of order k equal 2, okay? Because you only take pairs. You can take 2 pairs for k uples, and then build all of course here it will be all the selections of k uples between 1 and n. And it is quite classic that the behavior of such a degenerate U statistics is OP to the power k to the power minus k over 2. So in the case of k equal 2, you get a rate like 1 over n. Okay? But our U statistic was not so simple, because in addition to that you had the U statistic depends on the sample size, because it depends on the bandwidth, and the bandwidth depends on the sample size. What we usually ask is the bandwidth to decrease to 0 with the sample size. And then what was proved in 84 by Peter Roll, and very much improved in the sequel by other people, is to try to understand what will happen with such quantities when n grows to infinity. And it turns out that the rate of convergence is no longer 1 over n, but it's more like so OP depends on how it's in our case the rate. If h n may have a normal limit, there's not the U statistics. the U statistic, may have a normal limit, normal weak limit. Usually, if this does not depend on n, the limit of the U statistics is not of the normal type. It's more is centered by the mean, but here the mean is 0. It will be more a weighted sum of chi squared. But under some conditions, if h depends on n, then you recover a normal limit. And this is exactly these conditions that are satisfied in the case of our test statistic, and we come up with a central limit theorem, as I said at some moment. And so the test statistic, based on smoothing, we said that behaves like a Gaussian random variable under the null hypothesis. May have or will have, well, when h depends on n, the U statistic may have could have a normal limit under some conditions, and these are satisfied in our framework. So that is why we said this is behind all what we said yesterday.
So if h doesn't depend on n, then this is not normal limit, the sum weighted sum of the squares?
Yes, if h does not depend on n, the limit is more complicated.
But we can choose a way how it depends on n, bring it back, or for any...
So the central limit theorems we're using, it was stated at some point here, and we had some conditions of, sorry. So this is the statistic, with this is h, this is hn function, and the result says that if h goes to 0, at the same time not very fast, then you will have the normal limit. In these writings, h is a sequence decreasing to 0, satisfying this condition here. Maybe it's not the weakest possible. Maybe we can get rid of the logarithm, but not more than that, probably. And then h is deterministic and decreases to 0. Then you have a normal limit for the U statistic for this one. But the rate of convergence, please notice that the rate of convergence, look at the factor here. The rate of convergence is no longer n, that is n times h to the power q over 2, which means it's slower due to the h. Okay? When you fix h, and you get something which does not depend on n, you no longer have normality, have other type of limit, and the rate of convergence will be 1 over n, if you are degenerate. Okay? Good. So this is what we did, and we tried to understand how this behaves. How this behaves under the null and under the alternatives. So we stop more or less at this point, and we try to do some comparisons to say which test is better than the other. And there were some discussions about this between Spokane and Gumbev. This proves that the topic is still hot, and of course this depends very much on how you choose a bandwidth. But first, let's try to, I don't know if you tried to understand where is this coming from, this rate, these conditions about convergence. Just to see if you tried to understand a little bit. Could you imagine why? Sorry, I lost it. Just a second. No, I lost it. Where is? Yeah, maybe here. There are two types of conditions at some moment. I said that square root n, Rn, should go to infinity. And this is for empirical process approach. in square root and h to the power q over 4, Rn goes to infinity for smoothing based approach. For alternatives that look like y is equal mx theta naught plus Rn delta x. Okay, this was the so-called Pitman or directional alternatives. I don't know if it's clear where these conditions are coming from. We may try to remember what, at some moment, we looked at a quantity that we called, I think, m theta, and x, no, mx, I think we called it, and it was 1 over n, the empirical process approach, it was 1 over n, and it was yi minus mxi theta naught. Here I forgot, sorry, I forgot the epsilon, of course. We should still have an arrow term, yeah? And the expectation of epsilon given x is 0. Okay? So minus Rn delta xi, indicator of x smaller equal to x. So if you consider the statistic, what will happen is that you will, this is the statistic that one would consider it for doing this approach. What will happen is that for doing the empirical process approach, you still get epsilon I. That is sorry, just a second. Yeah, no, sorry. When you build your statistic, you don't have this, of course. You build your statistics, what you have is something like that. Imagine that you know the theta 0. Let's say that you don't estimate it. You have it. Let's say that you have it. And what will happen here is y this time is okay. We can. This is the true statistic one can build, and this is nothing but xi theta 0 plus epsilon I plus Rn delta n. Sorry, Rn delta x minus mx hat theta. Sorry, x theta hat I, indicator x more equal than x. Okay? So, what did you get in addition to what you get under the null hypothesis? So, you will have this a part that you find it exactly like this under the null hypothesis, which is mxi theta 0 minus m xi theta hat plus epsilon I, and now you have an additional term that is times the indicator. Now you have an additional term that looks like this. Okay. So this is exactly what you get when you are under the null. This is like under H naught. And you have an additional term under the alternative that is this one. So this behaves like, this would behave like 1 over square root n. Central limit theorem, and for epsilons, and the fact that theta hat estimates theta 0 at square root n rate. So if you want your test to detect the alternative, what should you need? You should need that this is larger than that. Okay? Otherwise your test statistics will not go beyond the critical values, so you need this quantity here to be larger than that. The rate of this quantity should be larger than the rate of this quantity. And if you look at 1 over n sum of the deltas, all what you can hope is that this is bounded in probability. You cannot hope that this will go to 0 because delta is not 0. So Rn could go to 0, but not faster than 1 over square root n, because otherwise the second part will be smaller than the first part and you will not detect the alternative. So exactly this is the reason why you ask Rn to be decreasing slower than 1 over square root n. Okay? Where is coming the other condition? It's clear where is coming the other condition?
Sorry, can you please repeat this? So, okay, I see the rates, but why you say that the rate on the right hand is Rn?
Well, this is basically Rn times something that is times something like let's call it delta, capital delta, and capital delta. All what you can hope is that this.
Yeah. So, what's the problem? The rate is the same in both.
Well, the idea, if you want your test to detect the alternative, this will give you the critical values, because this is exactly what you get under the knob. And this should be larger than this part if you want to go in the rejection region. So you should have that Rn is larger than 1 over square root n. Okay? No? This behaves like 1 over square root n,
Yeah, that's fine.
and this is exactly what you get under the null hypothesis. So the behavior of this quantity gives you the critical values. So the statistic you would like to be larger than these critical values than to reject. Then you have to have a leading term that is more important than the one that gives you the critical values. Okay? Let's try to understand where is this coming from. You tried to see where is this coming from? No? Maybe? Well, let's keep the same. But now let's go to this, let's call it Q, Qn, 1 over n, n minus 1, h to the power q. And then what you estimate is, again, what you put in your test statistics is theta naught plus epsilon I minus well, it's not very easy here. Could you just stop it a little bit? Just not stop it, but for instance, put it there. Okay? It would be much easier. Huh? So now we have more space. Huh? Oh, they will believe that we are watching a movie, huh?
A lot of action.
Yeah. So I think I called it Tn. Tn was something like 1 over, well, T hat doesn't matter. It was something like this. So when you build it, it will be mxi theta naught plus epsilon I plus Rn delta xi. This is yi. Yeah? And you subtract what you estimate from the model, and then you're doing the same with j, and then you put kxi minus xj over h, isn't it? This is what you get. And if you look carefully to that, here is an Rn. If you look carefully to that, then you may get several terms. So it's let's put this one and this one, put it together. So you may get, and let's call this difference, let's call it, I don't know, something like that. Okay? So delta mi, just to simplify notations, k h I g. I simplify notation, I say that kxi minus xj over h is khig. This is one term. Then you have another one that is 1 over n minus 1 h cubed, sum I different j, epsilon I epsilon j k h I g. And then you have other terms, something like 1 over n minus 1, h cubed, I different j, and then you have something like delta mi times epsilon j khij, and this I think it will appear two times by symmetry. You have from both sides, we have it from here, this delta times epsilon, this delta times epsilon, so you have it two times. Then you have another term that is Rn, n minus 1, h cubed, and then you have I different j, delta xi, gradient mj, khij. And I think this one comes also twice, because you have the symmetry. And then I think there is two more left. So you have 2 Rn n minus 1, h q sum a different j, epsilon I, delta xj, khij. And finally, you have another one. Let me put it here. Rn squared over n minus 1 h cubed, delta xi, delta xj, kh, hg. I think we did not forget anybody, no? You have 1, 2, 3, so you have 6. Now let's try to understand what happens with these terms. Let's try to understand. What is the order of this difference between this and that? If everything goes okay, and you estimate the parameter at the rate 1 over square root n, then you get here something like 1 over n. Okay? And of course, 1 over n minus 1 hq sum of just of the case, this will give you an estimate of the square of the density. So the expectation of the density, so the integral of the square of the density. So I think that everybody will be happy if I say that this should be 1 over n. Okay? Again, I think that everybody will be happy if I say that this should be Rn squared, because delta xi, delta xj with k here, you cannot hope too much about you only hope that it will converge to a positive constant. Yeah? So the convergence to 0 will be given by this rate here in front. Then this one will be given, the rate will be given by the central limit theorem, and this will be, as it was written at some point, this will be an OP 1 over n h q over 2. That's it? Okay? This is the central limit theorem that tells you that you have to normalize by this in order to get a normal distribution. So this will be the rate for this epsilon I, epsilon j. We can continue in this way. Probably there are two more that we have to look at it. What will happen when, let's try to understand what will happen with the last two ones. So if you look at this one may be simple to understand. Here you have the rate given by the parametric estimation error, so it's 1 over square root n. With an n in front, this will be more or less easy to see that it should be something like that. The rate of convergence. Yeah? So, what about this one? Well, this one, it's like when you have n minus 1, you can write it 1 over n epsilon I, and then a kind of function of xi, where this function is 1 over n minus 1, sum j different I, of delta xj kh, maybe there is a h minus q somewhere here, kh ig. Okay? So, this is more or less, it will converge. I think now you have, you did several times this type of non-parametric calculations. Will be close to some function phi. So finally here, deduce that this should be something like OP1 over square root n. Yeah? Or OP1, because epsilon is centered and is of 0 conditional mean. Okay? So this is of 0 conditional mean. Here you have a function that depends only on x. So this is like a usual central limit theorem for non-identical, independent random variables. Or if you don't believe, just simply compute the variance of this, just admitting that phi n is almost 4. Of course, at all these considerations, you can simply compute variance of all these quantities and deduce the orders. You just try to do some heuristics to have a quick idea about what the orders might be. So at the end of the day, this guy here will be something like OP are n over square root n, yeah? So the last guy is who we missed somebody? Oh yes, we still have this one, yeah? I think we missed somebody. No, we didn't.
Yeah, you did.
Sorry?
Yeah, you did in the lower left corner.
This one?
Yeah, I don't think you have to estimate for that.
So this one, you have here the parametric rate, and then you have the epsilon which is centered. So just look at the Taylor, just think at the Taylor expansion. Here you have a real gradient times theta hat minus theta 0. And if you admit sufficient regularity, you may say that delta mi is something like the gradient of m taken in xi and theta naught times theta hat minus theta 0, and that perhaps with a minus the way we define, plus something that is smaller order of theta hat minus theta 0. Yeah? If you allow some, you don't really need all these regularity conditions, but just to get a flavor about what would be the amplitude of this. So finally, this one should be also of rate 1 Rn over, sorry, this should be something like 1 over n. Okay? Because of theta hat minus theta, and because of the same type of argument as we used. Well, at the end of the day, what we get is OP. You have something 1 over n, you have r over square root n, you have 1 over n hq over 2, you have rn squared. So what would you like to do? Which one you still have under the... Well, anyway, Rn is certainly smaller than 1 over square root n. Even much smaller. Could not be smaller or equal than 1 over square root n. Could not be faster than, sorry, could not decrease faster than that. Which means that between these two, you may forget this one. Okay? Anyway, you know that h goes to 0. So between these two, you may forget this one. Okay? So at the end of the day, you have this term plus a term which is as large as Rn squared. But
we can drop the 2 because Rn is lesser than 1 over root of n.
it is exactly what we try to understand why. It is exactly what we try to understand. Why we come up with this rate. Well, everything what we understood for the moment is that probably we cannot have Rn faster than 1 over square root n, because then everything is negligible, you will not reject. But let's try. This will be the leading terms. This one is the one that gives you the critical values, because remember this comes from this piece. So this one is exactly what you have under the knob. So this will give you the critical values. So what would you like to have is to have this larger than this one. So you want Rn squared over n, sorry, times nhq over 2. You would like this to grow to infinity. Which brings us to the condition that Rn and hq over 4 should grow to infinity. And this is a condition that is on the window. Okay? This is the way you may understand by simply calculations of variances. Finally, you may understand, and admitting that you have a square root consistency to the theta 0. And of course, there is still a trick, but I'll let you. In fact, this square root n consistency of the theta hat when you are under the alternative. In order to obtain it, you need an additional condition. And the additional condition is that delta is orthogonal on the model. Is what Spokojny said yesterday, I don't know, maybe you were too tired. We have to ensure that this plus this is not in the model. Because if it is in the model, then you get some estimate of theta, and you will not see any alternative, because you are in the model. So the way to say that you're not in the model is to say that this is orthogonal on the model. And this orthogonality condition, which is the expectation of delta times the gradient of n with respect to theta, this orthogonality condition will be enough to ensure that theta hat minus theta 0 is OP 1 over square root n if expectation of delta x, the gradient with respect to theta of mx theta naught, is 0. So if you have this condition, then you have the square root n consistency to theta naught under the alternative. So everything what I told you would work. if you don't have this condition, things does not change much, because then you have, of course, what you should do is not to put everywhere theta 0, but to put the limit of theta hat in the model, because even if the model is misspecified, most of the time what will happen with the estimator is that it will converges to some value in the model. The difference between some value in the model and theta hat will converges to 0 at the rate 1 over square root n. If you don't have this orthogonality condition, the only difference is this value in the model will move. So, to avoid handling such situations, these simple conditions is what you usually put. To say that anyway, even under the alternative, you will converge to theta naught. This is a way to concentrate the analysis of your test on the performance of the test to detect alternatives, not to see what happens when you move in the model. You are very little interested in what happens when you move in the model. What you want to know is what happens when you are really orthogonal, you have a departure orthogonal from your model, and you want to study this pure analysis only about the departure. If you don't have if your model is not orthogonal, you go in this way. What will happen? You do not estimate. You will probably estimate something here, and you don't need. What is important to know is how performant it is to detect that you are not in the model, not that you are moving in the model. So a way to separate effects is to impose this condition. Okay?
So it's not restrictive in the sense of...
It's not at all restrictive. It's just, if you don't put it, you will have two effects. One, that you are no longer estimating theta naught, you're estimating something else. You will estimate something like, I don't know, theta n star that moves in the model, and theta hat minus theta n star, this will be OP 1 over square root n. So you combine two effects, will not change too much.
Just to summarize, so what are conditions? So we need something like Taylor for M, the gradient of M is bounded everywhere or something.
Yes, a form of Taylor. You may get it even if M is not differentiable with respect to theta. For quanti-regression, for instance, you have it. Even in quanti-regression, the moment conditions are written like an indicator. So you still have this type of approximation by theta hat minus theta 0. But roughly speaking, you need a Taylor for the M with respect to the parameter. And you need, to simplify your life, you impose something like this, but this is without loss of generality. And then we just understood where this conditioning is coming from. Okay? Okay, may I put it back? Maybe some of you were aware about all this or not. It's not very complicated. So let's say that we understood where this is coming from. I don't know if you had the time to look at the paper of Spokane and Horowitz. I told it to you now. Well, maybe I would like to do. So there are two papers. This is the one of Spokane. You may have it in working paper here. And I told you that about the choice of the values as being something a supremum with respect on a grid. Well, the statistics is not exactly the same one, but just read this part. It should be this is the idea. And the second paper, it's a paper, a more recent paper. Of Guérin Laverne, Annals of Statistics. Also, the first one was in Econometrica, and they are doing a similar idea of maximizing, selecting H on a grid, but instead of using Spokane's idea just to maximize TH, they introduce some penalty to introduce some penalty with respect to some favorite H naught that they would like to select in order to... H naught is a selected sequences of H, and the test will be oriented to detect such type of alternatives that for which H naught will be optimal, but the test may adapt and select another H if you proceed by a maximization over a grid. This idea of penalization with a privileged quantity will come. I will come to this a bit later, but in another context, not for the bandwidth, but for the projections. But this idea, as you see, is quite familiar in the statistical and econometric literature. So for people wanting to know, willing to know how H has to be selected in such procedure, in such testing procedure, please go to these two papers and see the results. We discussed quite a lot yesterday that this data-driven procedures adapt to the regularity of the alternatives. If you are in a Pitman case, then the selected H will be very, very slow, of order log squared to the log n. And finally, the two conditions on the Rn are finally not very far one from the other. So you should not believe that the Bjerre's test is better than the smoothing based. With such type of data-driven selectors for the bandwidth, you get almost up to a log term, you get almost the same power against such kind of alternatives. On the contrary, if you have other types of alternatives where the frequency delta changes, so delta change with the sample size, then the Bjerre's test may have trivial power, that is, the probability of rejection would be equal to the size of the test, while tests based on smoothing can detect such alternatives, provided that H satisfies an appropriate rate. So about how to choose the bandwidth and why smoothing tests are, mathematically speaking, much more interesting than empirical process-based tests, you can find in these two articles a lot of arguments. So please look inside. Yeah, it's what I was saying here. Okay. Well, there is a third paper that I mentioned about how to choose the bandwidth. It's a paper of Gao and Gagos in JASA in 2008. They have a different approach. Roughly speaking, they consider the case of such alternatives, and they look at the best H by studying the adverse expansion of the test statistic and trying to make this adverse expansion to take the optimal H such as the statistic to be the closest possible to the normal asymptotic approximation. The problem with the paper of Gao and Gabus, of course, is that this adverse expansion, the coefficient depends on unknown quantities. So you have to estimate, of course, this constants in the adverse expansion, and then you may optimize the values to get the best normal approximation. But at the end of the day, it's not sure that this will work better than what did Geronaven and Spokojny and Horowitz. So it was published in JASA. The proofs are not inside. They are in so-called supplementary materials. But well, I would like to see how it works in practice in extensive comparisons. But you should know that these are not very many methods to choose the bandwidth. Basically, two categories, and these are the three references for that. Good. And this is a kind of explanation is what we said yesterday. In fact, the kernel smoothing, the empirical based process approach is a kind of kernel smoothing testing, but where the bandwidth does not vanish. So, since the bandwidth does not vanish, what will happen is you may lose some high frequency departures from the null. That explains why empirical process testing can perform very badly against such alternatives. Thing that was proved by one more time by Spokojnian, Horowitz, and Gabriel Lavergne, which shows precisely that the empirical process approaches are very bad when you have delta depending on the sample size. Okay, so all this it's a kind of state of art about classical approaches of checking parametric models. Let's try to see how this idea could be extended to non-parametric significance testing. Very briefly, let me recall what the problem was. So you have a response variable y, and you have two sets of explanatory variables, x1 and x2, and you would like to perform non-parametric regression on x1 and x2, but of course you wonder if it's worthwhile to smooth on x2. You wonder if smoothing on x2 is not exactly the same like smoothing only on x1. In other words, you ask this question here, which is like saying, is x2 significant for the non-parametric regression? And the way, oh, I see a small mistake here. Here is a square bracket. Here is a square bracket. The way to do this is to put under the form of, you see here, the expectation of y given x1 and x2 equals expectation of y given x1 is equivalent to this writing here. And now, of course, what is inside the brackets will be our epsilon. And with this epsilon, we will try to build the same U statistic to get the test. And I said at some point that this epsilon, you have to estimate it. So this epsilon, you have to estimate it. And in order to avoid denominators, you see that, so epsilon here is, let me write, epsilon would be y minus expectation of y given x1. This is the residual of the non-parametric regression under the null hypothesis. You cannot avoid building this object because under the null hypothesis, if you want to check the significance, you have to get the residuals under the null hypothesis. But what you could avoid is to estimate this object that has a denominator, because you can easily understand that this is exactly the same problem if you multiply this residual by any function of x1. And you may choose one nice function of x1 that avoids you problems with denominators. Okay? So now you understand that you only have a density estimator times y, and here you have the regression times the density. You don't have there are no longer denominators in your estimates. Okay? And then, of course, if you follow exactly the same idea as in the previous case, what you need now is to look at the quantity expectation epsilon given x1, x2, and some weight function, and the way you take this weight function is to avoid denominators here, so you put here the density of x1 and x2. Okay? So you have two multiplications. One is to compute the epsilon and to avoid denominators at this level. And another multiplication, another trick is to multiply here by this density to avoid denominators at the test statistic level. Okay? So doing these multiplications, you avoid handling denominators and you avoid usual problem. What is very nice with testing is you can do all this because the problem is completely equivalent. You cannot avoid these denominators when you estimate. It's very funny that for testing the life is much easier. For estimation, you have to always to pay the price of the denominators. If you want a regression, non-parametric regression, you always have to divide by something. You cannot avoid this. But for testing, you are not forced to do that. And from some point, testing is a much easier life than estimation. Okay?
You can somehow invert the statistics for the estimation.
There is a way to do it, and this is another topic. Maybe I'll come another time to talk about that. You can use exactly the same test statistic to estimate parameters, but because everywhere where we are talking here is, this is some work that we try to do with Spokojny. Everywhere where here we take the estimator to be something that is coming from somewhere, like for instance least squares or whatever. But you may say, why not using the same test statistic and try to find an estimator based on the same test statistic? And the idea is, yes, you could. You just minimize this test statistic with respect to theta, and by the construction of the test statistic, you should get an estimator that is under the null. That is, if the model is correct, you should get something that converges to theta null. And this is true. This was proved in another paper we try to extend. Because of course, this modern tools of non-asymptotic results, we try to do things at finite distance to get quantities. So it could be used. And then you avoid denominators, which is pretty nice. But for parameters, okay?
And here conditional expectation.
Here, to estimate conditional expectation is more tricky. It's not the same story. But for finite dimensional parameters. Okay? So now, yeah, if you want to get an estimate of epsilon I, then this is epsilon and n minus 1. Sorry. There should be a mistake here. It's only n. So it's 8. Another value is g to the power some k difference I, yi minus yk, some kernel of x1i. This is y and x1j over g. So this would be an estimate of this. If you want to estimate this. Sorry?
What is the power of j?
P1. P1 is a dimension of, oh sorry, Q1. Sorry. Q1.
And by A,
It's care.
it's not
Is another kernel.
um,
Yeah, because you have, when you check significance, you have, as I said, two smoothings. One smoothing is at this level. It's like we did like till now with epsilons. Here you have the k kernel. But to compute the epsilons, now it's more tricky than in the parametric case. Because you have to check to get the residuals. The residuals are obtained after smoothing. So you have two smoothings. One for the null, and you may do it in this way. Now, it's not the only way that you could do it. And the second one is like all we did previously.
and G is another one.
G is another balance. When you have conditions on the two balances. I'm working with a student, a PhD student I have in Rennes. He's studying this problem. and he's trying to put in place a test where you no longer smooth in the second test to avoid smoothing in dimension Q1 plus Q2, which is a big problem. Which is exactly the smoothing that you would like to avoid, because the smoothing under the null you cannot avoid it. If you want to check a regression, you have to estimate your regression and check the residuals. This you cannot avoid. But the question would be, could you avoid smoothing in the test statistic? Could you avoid this? And the answer is yes, you could. Already people used the empirical process approach to build this statistic with residuals estimated in this way. What is a pity is that if you use here the empirical process approach, like we did at the very beginning, remember, you lose the normal critical values. Okay? You get in the empirical process approach where you don't have, you converge to a Gaussian process, and then you have some critical values that you have to determine by simulations. Okay? But the idea then would be, given that you smooth already here, could you smooth with the lowest price possible and still find a standard normal distribution? And the answer is yes. You smoothing one more time, only in the first dimension here, you build a statistics that preserves an asymptotic normality for the test, and you avoid. So the paper where you apply empirical process approach to this with epsilon estimated in this way was published in 2000 and I don't know. Remember, in Annals of Statistics by Delgado and Gonzalez-Martinez. And with my student we showed that in fact doing in this way with empirical process here is unnecessary. With an additional smoothing only in the dimension of Q1, Q1, yeah, you can recover the normality. This is a quite nice trick that we found.
Q1 or Q2? I mean that doesn't depend on Q2?
No, this is quite surprising.
Yeah.
You smooth exactly in the same limit, but one more time.
Okay.
And you don't smooth in X2. And you recover everything. You have a consistent test. It's quite intriguing. But it's really surprising, but nice. Okay. So all I said is here. And of course then, if you look at Piedmont alternatives, here you have Q, and Q is Q1 plus Q2. And if you use, yes, please.
I just wanted to ask if we will have some code breaking.
Oh, I'm sorry.
No,
just after this, just before going to, yeah. Just before going, yeah, just read this and we'll go to the computer. Yeah, I thought that you are concerned about convergence rate. But it was convergence rate to the coffee shop. Unfortunately, the test converges very slowly to the coffee. So here with Q1 plus Q2 variables, you see that you pay a price here on this power. So what people usually say is a curse of dimensionality. Here more x2 is dimension of x2 is large, less powerful your test will be. But with what I'm saying to you that if you avoid smoothing in Q2, like in the paper in the annals with empirical process, then you may put here Q1. Okay? You cannot avoid Q1 because you smooth under the knob. You cannot avoid it. You avoid it in the parametric setup because it was parametric. So it was no price to pay. But in the non-parametric significance setup, you cannot avoid Q1. So Q1 will have also always here. This is a paper of Delgado and Gonzalez-Martinez. But what do they lose is the standard normal distribution under the knob. With the nice idea my student found, you can keep the same Q1 here, and recover the normal distribution. I'm trying to send it to you to present this someday. Okay.
So if you smooth Q1, then another one Q1, then still it's H power Q1 over
Yeah.
4.
Yeah, since you don't smooth in Q2, you don't pay the price of the banks in Q2. So I propose to have a coffee break and then to go. Okay? Thank you.